Let's use this. Let's figure this out. Let's use this formula, Max formula, Max. He has a cool name, Max Gilbert Ernst or something like that. It's a pretty cool name. I'm just gonna look it up right over here. There he is, Max Carl Ernst Ludwig Planck, a German physicist. Right. Einstein is obviously an Austrian, German-born physicist, and then Gilbert Lewis is actually an American physicist or chemist. So it's a pretty international venture we got going on here. So how much energy is carried by the photon of red light that has 600 nanometers? It's probably orangish. I remember red light is around 700 meters. That's a cutoff point, so it's a pretty big range. Actually, if you think of all the visible light, red is the biggest pack, and then it becomes orange, then yellow and green, violet, and violet's light, like the smaller amounts, like a pretty small amount of wavelengths there. I want to express my answer in both joules and electron volts here. So I'm going to do the calculation twice. So you can either find the joule version, then convert that into electron volts, or vice versa. You can find the electron volts and change it into joules. But I'm just going to do the calculation twice with the two different H values. Now, you'll realize if you try to do it one way, so if you say you found the joules and change it into electron volts, or use just the H value to get the electron volts right away, the numbers are going to be slightly different just because you're compounding a rounding error twice. Both H's are rounded, so you use one, get a rounding error, then you use the conversion of 1.6 times 10 to the negative 19 to change it into one of the other forms, such as joules or electron volts. Then now you compounded an error, like a rounding error, twice. Right? So now we have extra error, so that number is going to be slightly off. So by doing the calculation twice with two different H values, you only have the one rounding error when you get to the end. So using the H values independently at different times gives us better values. So I'm going to do it twice here. You'll see. So my first one, we're just going to write here what my wavelength is. So it's 600 nanometers. So I'm going to change that into regular meters. And the first one here I'm going to go for joules. So I'm going to use the 6.63. So I'm using the formula. So I'm using the formula HC over lambda. Now, Planck didn't have this formula to start off with, right? His formula just says HF. Where does HC over lambda come from? Well, HC over lambda comes from just combining this and the universal wave formula together. So if I just said, okay, F is equal to C over lambda, if I just put these two formulas together, okay, if I just substitute the F in that first formula, I can get that. So I can get NH bracket C over lambda, and it simplifies down to NHC over lambda. So that's that part, HC over lambda. So that's where that comes from. So rather than changing that into frequency, I could just use the HC over lambda formula to do it for me. Okay, so I'm going to do the joule one first. So my speed of light here, and I'm going to divide it by my wavelength. I'm going to make sure that's in meters, because the speed of light's in meters, joules has meters and kilograms and all sorts of things in it. So I'm going to make sure all the units match each other. Excuse me. Okay. So I'm just going to type this all in my calculator. And we're going to get an energy in joules of 3.32 times 10 to the negative 19 joules. Okay, so it's a rather small number. So what I'm going to do now is I'm going to do the same calculation, HC over lambda, but this time I'm going to use the 4.14 number to the negative 1 or 15 electron volts seconds version. If you want to do the unit analysis, you can. I'm not too concerned about the unit analysis at this point. Just assuming that if you keep your units in their base units, you'll get the proper thing out. So I'm just going to go change this number here. 4.14 e to the negative 15. Yep. So we get 2.07 electron volts. So you look at those two numbers and you say, okay, which is the better of these two numbers? Do I like the electron volt better, or do I like the joule version better? Right? So for the communication purposes, the electron volt version is a much better number to use. For the mathematical part later on, like if I need to find what's the momentum of this massless particle, which is kind of a weird concept because momentum is mass times velocity, but it has momentum. It's strange. We'll talk about that later on, something called Compton's law or Compton's effect. Or if I want to find the energy transfer to an electron, then to find out the electron speed afterwards, I'm going to have to use the joules to do all that calculation. And there's some specific formulas on the formula sheet where it mentions an H, but you have to use the 6.63 version of the H to do that, and I'll talk about those later on. But for communication purposes, the 2.07 electron volts is the perfect number to use. And most of the time when I ask on a test, because that's a nicer number to type into the boxes or to write down, that's what I'm going to expect, right? Because they usually end up being nicer numbers. What's the energy of a photon that has a frequency of 4 times 10 to the 14? So it doesn't specify what kind of energy. So for communication purposes, I'm just going to use just the 4.14 number, the electron volts, to communicate this. So I don't have to do the math twice. I won't do it twice. Perfect. Notice that this is per hertz and this is seconds here. Those are going to cross each other off. So I do get electron volts out on this one through just a simple unit analysis here. Okay, and so I get 1.66 electron volts on that one. Okay, electron volt can detect as few as 500 photons of light. So this is where you're thinking, okay, now they're talking about multiple photons. So that's an N value here. So I'm just going to mention that. That's my N value. It's 500 photons. The eye is most sensitive to light, having a wavelength of about 510 nanometers. What's the minimum energy that the eye can detect? Okay, so there's two ways to do this one. Usually the way I would do this is calculate the energy of one photon, then just times it by 500. But if you want to combine it all together and say, okay, the energy that the eye can detect is going to be 500 times, that's the N value, of H times F. That's the formula that's at the top there, where Max Planck says. But you can also just change that to hc over lambda, because we have wavelength here instead. So wavelength is 510 nanometers. I'm going to leave this in electron volts because that's a nicer number to communicate here. It's probably going to end up being nicer than the joule version. So I'm just going to put all my numbers in. 500 photons times the 4.14 times 10 to the negative 15 electron seconds times the speed of light, divided by 510 times 10 to the negative 9 meters. Sorry. Okay. Let me just type all this in my calculator. It's a lot of typing in calculators here. Okay, so one photon, I haven't done the times 500 yet, one photon is 2.435. I'm just going to write that down here. So I just did the one photon part, so it's just the hc over lambda, and I got 2.435 ... electron volts. Now I'm going to times that by 500 because your eye can detect as low as 500. So it can detect about 1,117.6 electron volts. So I'm going to change this to 3 sig digs. Now electron volts, usually they don't use scientific notation for electron volts. So you're going to change the prefix here. So I'm going to move it over 3 spots. So you get 1.22 kilo electron volts. Now if you want, you could just put that in joules too if you needed to. But I'd like to communicate these with electron volts. Okay? How many photons of light would there be to deliver 10 joules of energy? 10 joules is a big number in terms of photons, right? So if you think about this, what they're looking for in this formula, they're looking for this question. They're looking for how many photons would I need to get 10 joules, right? So if I look at just the one photon, so I'm just going to do one math for one photon here, which is just going to be hc over lambda. I'm not going to use the HF version. And this is in joules, so I am going to have to use the 6.63 number. Okay. 3 times 10 to the 8 divided by 550 times 10 to the negative 9. So I'm going to type this in really quickly here. Okay, so I get a number that's 3.6163 ... times 10 to the negative 19 joules. So it's a really small number. That's one photon. 10 joules is gigantic then, right? So I want to know how many of these smaller numbers fit into that big number at the top there. So if I were to rearrange that for n, it would be the energy divided by HF, which we found. So 10 joules divided by this 3.16 or 6163 times 10 to the negative 19 joules. So I'm going to go 10 divided by this number in my calculator, and we get a big number. You always get a big number when it comes to the number of photons. Don't get anything small. You can't have half a photon. You can't have 10 to the negative 19 photons, because those are not whole photons. Photons have to be wholes. So we get 2.77 times 10 to the 19 photons, because the joules are going to cancel each other out. And this would be technically, if you think about the units of that bottom number, it's how many joules per photon, right, for one photon. So cancel out and kind of flip up to the top, and then that's how many photons you would have. So how many photons would be emitted from a laser pointer? So imagine you have a little laser pointer like this one. Boop. I don't know. I don't want to put it at the screen because I don't know what's going to happen if I... Oh, well, that's kind of fun. All right. How many photons are coming out of that laser pointer every second? It says here for each second. Sometimes I mentioned maybe 10 seconds or a minute or an hour or something. In this case, I just went for 10 seconds or 1 second. So right now I have my time being 1 second for each second. We have power here. So this is capital P, 0.400 times 10 to the negative 3 watts. I'm just going to change it to regular watts there. And then we also have a wavelength here. Let's just change that to regular meters as well. See, those are not proper scientific notation, but for math and my calculator, it just makes it easier to type those out. So, yeah, is that the same as this one here? Well, that's around that. This is 630 to 680. What do you think about that? Okay. It's a bit more orangey red light laser pointer. So how are we going to do this question? So it's very similar to the previous question. We want to figure out how many photons are released every second when you talk about power. Remember what power is. Power is work divided by time. Now this W is not watts or anything. The power is watts, right? So that's what the big W is here. So that's a different W. So I'm going to rearrange this. Or actually, I'm just going to say delta E over T instead, not to get confused with the W's. So I'm going to rearrange this for P times T. So it's P, which is 0.400 times 10 to the negative 3 watts times 1 second. What happens here is that this changes into joules. If you were to do the work, or the unit conversion on that one, ends up being just a joule. Okay, so that's how many joules every second a laser pointer pumps out. Okay, this is per second if you want to think that. Okay, how many joules per second. Now, what we're going to do here is do the exact same steps that we did in the previous one. Find how much energy is in one photon. So hc over lambda. So I'm going to use, because this is in joules over here, I'm going to use the 6.63 number times 10 to the negative 34 joules. 3 times 10 to the 8 divided by its wavelength of 600 times 10 to the negative 9. Okay, so I'm going to punch those in my calculator. I do it enough that I think I would store that HC into my calculator so I don't have to type it all out all the time, but maybe I just like typing things out. Okay, so the energy of this one photon is 6. Oh, why am I saying 6? 3. Okay, 3.315 times 10 to the negative 19 joules. Cool. This is per photon. So I want to find out the n again, just like the one previously. So I'm going to take, where am I going to put that? Maybe put that over here. I'm going to take that formula, E is equal to NHF. Rearrange it for N, which would be E divided by HF. And what we calculate, this HF is technically the HC over lambda. I'm just leaving it as HF because it's easier to write. So I'm going to take the amount of joules that we have, which is a big number in comparison, right? And divided by the small number here. This is per second here. So the joules are going to cancel out. Things are going to flip around. This will end up being photons per second if you were to do all the unit analysis there. So I'm going to take this 0.4 times 10 to the negative 3 and divide it by my number. And I'm going to get 1.21 times 10 to the 15 photons per second. There you go. Okay. Oh, this video is going to be a bit long. It's at 20 minutes right now. Oh, sorry about that. Maybe I'll split it into 2 for you, or I haven't done already. So we have this spectrum here. Now we can add this energy amount into this spectrum. Like we have wavelengths along the top here. So nice little wavelengths here. So nice little wavelengths along the top here. You notice that the longer wavelengths in the radio waves, the shorter wavelengths over here in gamma rays. You got visible light being this tiny little piece right in the middle, right down there. Well, not really the middle, but somewhere down the middle. Radio, microwave, infrared, visible, ultraviolet, X-rays, and then gamma rays. Down here we also have to compare the frequencies as well. You notice that gamma rays have large frequencies. Radio waves have low frequencies. Like, to the power of 6 is a pretty low frequency. Like visible light's to the 14, 15. That's still in the visible right there. But now we can add in this extra piece, this photon energy. And these are all in electron volts down the bottom here. Now, because of the formula, E is equal to HF, if my frequency increases, my energy increases. So you notice that if I have high frequency, I have high energy. If I have low frequency, I have low energy in electron. These are all in electron volts, you can see. So about visible light here, visible light is around that 2 or 3 electron volt range. You see just in the infrared, you got the 1 electron volt range. So visible light is just a small little section there. But they kind of match up nicely. So frequency and energy are directly proportional to each other. But in the other formula, HC over lambda, they are inversely proportional. So this one goes up, this goes down, right? It's because they're inversely proportional to each other. One's in the denominator, one's in the numerator. So there we go. So at the end of that first lesson, the next lesson we're going to be talking about the photoelectric effect that was already discussed in one of those videos already. So I'll see you then. Bye.